It is arguably the most stressful piece of glass in your entire house. You step out of the shower, take a deep breath, and carefully place both feet onto that sleek, cold digital square sitting on your bathroom floor. Within exactly 3 seconds, a bright digital number flashes on the screen, telling you exactly how much your body weighs down to the exact decimal point. We step on these devices every single morning to track our fitness goals, bake a perfect loaf of bread in the kitchen, or weigh our luggage before a flight. But if you actually stop and look at a modern digital scale, it completely defies common sense. Think back to the heavy, old-school analog scales you used to see in doctors' offices or your grandparents' bathroom. When you stepped on those, you could physically hear the heavy metal springs creaking, groaning, and stretching under your weight as a little red needle bounced wildly across a numbered dial. It made total physical sense, but a modern digital scale is completely silent. It has absolutely no visible moving parts. It is literally just a flat piece of tempered glass sitting on top of a plastic shell. So how on earth does a solid, immovable piece of glass physically feel your body weight? How does it magically translate the downward force of gravity into a highly precise digital number on an LCD screen? Today we are going to flip that glass square over, rip out the internal wiring, and break down exactly how a digital scale works, revealing the invisible microscopic physics happening right beneath your toes. To understand this everyday magic trick, we first have to bust a massive myth. When you step on a digital scale, it actually does move. You just cannot see it with your naked human eyes. The secret to this invisible movement lies in the 4 little feet resting on your floor. If you open up the plastic casing of a standard digital bathroom scale, you will find that those 4 feet are connected to a highly engineered component called a load cell. The load cell is the absolute heart and soul of the entire machine. In a typical home scale, the load cell looks like a small, sturdy, rectangular block of solid aluminum or steel. When you stand on the flat glass surface of the scale, your body weight is evenly distributed down into those 4 corners, putting immense downward physical pressure directly onto those solid metal blocks. Now, aluminum is an incredibly strong metal, but under the heavy force of human body weight, it does something fascinating. It physically bends and deforms. Because the metal block is so thick and sturdy, it only bends by a microscopic fraction of a millimeter. It is an incredibly tiny, completely invisible amount of flexing, but that microscopic bend is all the machine needs to figure out exactly how much you weigh. But how does the scale actually measure a bend that is too small for the human eye to even see? This is where we introduce the true genius of the system, a tiny microscopic component glued directly to the surface of that bending metal block, known as a strain gauge. A strain gauge is an incredibly thin, flexible piece of insulating backing with a microscopic metallic foil pattern printed right on top of it. This metallic foil is usually arranged in a tight, zigzagging pattern, running back and forth over itself many times, kind of like a radiator. During the manufacturing process, this tiny, fragile foil sticker is glued permanently and securely to the solid metal load cell. This permanent glue is crucial because whatever the heavy metal block does, the tiny foil sticker is forced to do exactly the same thing. If the metal block bends slightly downward under your weight, the top surface of the block stretches out, which forces the zigzagging foil sticker to stretch out and elongate as well. To understand how stretching a tiny sticker translates into a number on a screen, we have to look at a very simple rule of electricity. The scale uses a small battery to constantly send a tiny, safe electrical current through that zigzagging metallic foil. You can think of this electrical current exactly like water flowing through a garden hose. If you have a normal, relaxed garden hose, the water flows through it easily. But what happens if you grab both ends of that rubber hose and stretch it out as hard as you can? As the hose stretches and gets longer, the rubber walls become much narrower and tighter, which makes it significantly harder for the water to flow through the middle. The exact same principle applies to electricity flowing through a wire. When you step on the scale, the metal block bends, forcing the foil strain gauge to stretch out. As the foil stretches and gets longer, the microscopic metallic pathway becomes incredibly thin and narrow. Because the pathway is now longer and thinner, it becomes much harder for the electricity to flow through it. In the world of physics, this is called an increase in electrical resistance. The heavier you are, the more the solid metal block bends. The more the block bends, the more the foil sticker stretches, and the more the sticker stretches, the higher the electrical resistance becomes. It is a perfectly linear, flawless chain reaction of physical cause and effect. But the scale still has to turn that electrical resistance into a readable number. This is where the final component, the microprocessor, steps in to save the day. The electrical changes happening inside the strain gauge are incredibly tiny, often just a few millivolts, which is far too small to display directly. So, the scale uses a specialized electronic component called an analog to digital converter. This component takes that tiny, struggling electrical signal from the stretched foil and acts like a massive magnifying glass, amplifying the signal so the computer chip can easily read it. The internal microprocessor receives this amplified electrical data and instantly runs it through a mathematical formula. Because the scale was carefully calibrated at the factory before it was placed in its cardboard box, the computer chip knows exactly what that specific level of electrical resistance means in the real world. It knows that if the resistance increases by a specific microscopic amount, it equals exactly 150 pounds. The microprocessor performs this complex mathematical calculation in the absolute blink of an eye, completely translating microscopic metal deformation into electrical resistance, and finally into the bright digital numbers flashing on your LCD screen. What makes this technology even more brilliant is its incredible versatility. The exact same strain gauge technology measuring your body weight in the bathroom is currently being used all over the entire world in drastically different sizes. Tiny, hypersensitive load cells are used in digital kitchen scales to weigh out a few grams of baking flour with absolute perfection. Meanwhile, massive heavy-duty load cells the size of cinder blocks are installed under highway toll booths to instantly weigh 80,000-pound commercial semi-trucks as they drive by at high speeds. Whether it is measuring a single gram of coffee beans or a massive steel shipping container, the physics of stretching a tiny metal foil remain exactly the same. So, the next time you step out of the shower and nervously wait for those digital numbers to settle on the screen, you will know exactly what is happening beneath the glass. It is not just a magic trick guessing your weight, it is an incredibly precise, highly engineered system that physically bends solid metal and calculates microscopic changes in electrical resistance just to keep you informed about your health. Understanding the hidden physics inside these everyday objects takes the mystery out of our daily routines and gives us a new appreciation for the brilliant engineering sitting quietly on our floors. If this breakdown helped you finally understand your household gadgets, hit that subscribe button, give this video a quick thumbs up, and leave a comment below telling me what everyday machine you want me to explain next. Thanks so much for watching, and stay curious.